Chapter 4, Problem 55. When baseball players throw the ball in from the outfield, they usually allow it to take one bounce before it reaches the infield, on the theory that the ball arrives sooner that way. Suppose that the angle at which a bounced ball leaves the ground is the same as the angle at which the outfielder threw it, as in figure 4.55. But the ball's speed after the bounce is one half of what it was before the bounce. A. Assuming the ball is always thrown with the same initial speed, at what angle theta should the fielder throw the ball to make it go the same distance d with one bounce, the blue path, as the ball thrown upward at a 45-degree angle with no bounce, the green path? B. Determine the ratio of the times for the one bounce and no bounce throws. So for the givens, we have one ball being thrown at 45 degrees, which is the ball following the green path, and we have the velocity of the ball throwing the blue path as v, and once it bounces, the next velocity would be v over 2. So, since it is thrown horizontally, we are able to use the range equation, and we can start by using the range equation on the ball that is thrown at the 45-degree angle that's followed the green path. For simplicity, we get the distance equals the range 45 for 45-degree angle, which equals v initial squared sine of 2 theta, so it would be sine of 2 times 45, sine of 90, divided by gravity. And for the ball bouncing, we have to take into consideration the first path it takes and the second path it takes. So we'll split it up into R1 plus R2. R1 being the first path, and then R2 being after it bounces. So R1 is going to be the V initial of the ball times sine 2 theta over gravity plus, and R2, since the velocity is half of what it was in the beginning, you put V initial over 2, and that have that quantity squared, times sine 2 theta over G. And theta is the angle it makes with the ground when it's thrown and when it bounces, because both angles are equal to each other. Now for part A, what we can do is set both distances equal each other. So the distance and range equation from the green path equal to the distance and range equations from the blue path. So that'll be r sub 45 equals r sub 1 plus r sub 2. So seeing that sine of 90 equals 1, we can just get rid of that and put v initial squared over gravity equals r sub 1 plus r sub 2, which is v initial squared sine 2 theta over gravity plus a simplified version of v initial squared over v initial over 2 squared sine 2 theta over g, which simplifies down to v initial squared sine 2 theta over 4g. Now using basic algebra steps, you can simplify that into sine of 2 theta equals 4 over 5, and solving for theta, you get theta equals 26.6 degrees. Now for part B, since the flight of the path of the ball is parabolic, we can use the equation y final equals v sub yi t minus 1/2 gt squared. Since y final is 0, we can set that equal to 0. And since Vyi is just the vertical component of the velocity, you can rewrite that as V initial sine theta initial t and minus 1/2 gt squared. So if t is set equal to 0 is the time when the ball is thrown, then solving for t, you get t equals 2v initial sine theta initial over g is the time at which the ball lands. And for the ball thrown at 45 degrees, the ball that follows the green path, you put 45 degrees in for theta, and you get t sub 45 equals 2vi sine 45 degrees over g. And for the bouncing ball, we once again have to split it into two equations for the time it takes before the bounce and for the time it takes after the bounce. So before the bounce, we have t sub 1, which is going to equal 2v sub I sine 26.6 degrees over g plus t sub 2, which is after the bounce, 2 times v sub I over 2 sine 22.6 over g. Now this is totally going to equal 3v sub I sine 26.6 degrees over g. And just a reminder, 26.6 degrees is the value for theta we obtained in part A. And the ratio of the time for no bounce is you just take the bouncing ball time over the non-bouncing ball time, and you get 3vi sine 26.6 over g divided by 2vi sine 45 degrees over g, which simplifies down to 1.34 over 1.41 equaling 0.949.